Hi, this lesson is all about a geological technique that can be used to try and address some of the issues to do with climate change. And in particular, how do we remove carbon gases from the active carbon cycle? How can we put the carbon that we've extracted from the earth in the form of coal or oil or natural gas and put it back into long-term geological storage? It's a technique we call carbon capture and storage, or geosequestration is another name used for it. This cartoon sort of illustrates the basics of the idea. Hoovering the carbon dioxide out of the atmosphere, particularly from large single polluters like power stations, and injecting it back into the rocks where the carbon was extracted from. Now we're working on page 21 of your um, Theme 4 booklet. If you haven't already, you need to watch the video produced by the British Geological Survey about carbon capture and storage. There are several different settings where we can actually inject carbon into or carbon gases into the rocks, and they'll be safely stored for geological periods of time. These are shown on the diagram at the top of page 21. It is possible to put carbon gases back into hydrocarbon fields. If we think about it, the structures that allow oil and gas to accumulate to make a hydrocarbon trap will also be ideal for storing carbon gases, if like after their use. The right geology will exist in terms of a cap rock and a reservoir rock. There'll be pore space to hold the gas. The cap rock will prevent its escape. The structure will be there to store large quantities of gas within that. It is possible, as well as using hydrocarbon fields where we've extracted all the oil and gas, to use oil fields where perhaps production is starting to drop a little. By injecting the carbon gases into a declining oil field where the oil is getting harder to pump out, that can force more of the oil towards the extraction wells. A really good place to store carbon gases, though, are in coal seams, particularly really deep coal seams, ones that are so deep we're not going to be able to mine them out. And particularly as our energy diet is changing over time, coal is becoming increasingly a fuel of the past. But by injecting carbon gases into coal seams, those carbon gases will react with the coal and will actually solidify. So you can actually, you don't need to worry about the escape of these carbon gases into the atmosphere in the future. The last place we can store these carbon gases is in deep, salty groundwater. If you've got groundwater that's more than maybe, say, 800 meters deep, that water will have been in the rock a very long time. It will it'll have dissolved minerals within it. It'll be too salty for us to use, and also too deep for us to be worth pumping out. Pumping carbon gases to be dissolved in that groundwater will also be another effective store for them. So we've got these different types of settings. Let's look at an example of where these things could be put. These diagrams are cross sections through two real hydrocarbon fields in the North Sea. Brent hydrocarbon field is in the northern North Sea. Lehman hydrocarbon field is in the southern North Sea. It's just off the coast of Norfolk. So these are two real geological settings where oil and gas have accumulated, where they've been extracted for use. The question is, can these be used for carbon capture and storage? So what I'd like you to do is I'd like to evaluate each of these fields, annotate these diagrams. What's potentially good about these sites for storing carbon gases? What limitations might there be for using these? So, press pause, have a go at those now, see what you can come up with. Okay, let's have a look at some results of this. Let's start with the Brent hydrocarbon field. Brent is the, if you like, standard for North Sea oil. This is when we start talking about the oil price, it's crude oil from the Brent field that we use. You can see from this particular site, what we have here is an unconformity trap. We've got the reservoir rocks, which are Jurassic sandstones, and then a cap rock of this Upper Cretaceous chalk and clay. We can see that this site is relatively deep. These reservoir rocks are maybe 2.5 to 3 kilometers below the surface. So the chance of this stuff escaping is fairly low. We've got the right geology as well. Those porous and permeable sandstones that can absorb the carbon dioxide. There are some downsides to this site though. It is in the North Sea. It's not to say the engineering will be impossible. We certainly solved the engineering problems to extract this oil in the first place. But we would have to have some means of getting the carbon dioxide out, in this particular case, into the middle of the northern North Sea. If we contrast it with the Lehman hydrocarbon field, here we've got an anticline trap. It's actually a faulted anticline. We've got a very good trap here where the gas there, in this case, this was a gas field rather than an oil field, in the Permian sandstone, which is a desert sandstone, very high porosity, very high permeability, has a cap rock then preventing any upward movement. Notice as well the horizontal scale here. This anticlinal structure is huge, 10, 15 kilometers across here. The geology as well is almost perfect. We've got a cap rock here of evaporites. Evaporites are impermeable. They also, if you like, can flow a little, so they actually heal themselves if they get fractured. It's a tremendous cap rock. The sandstone I've talked about already. Also, just below that, we have the original source rock for the gas, which was Carboniferous coal. So if any gas is injected into that coal, it will solidify. Perhaps the biggest benefit of this particular field is the volume. This is huge, 1.6 times 10 to the 11 cubic meters. That's absolutely vast. 160 billion cubic meters. This field is also, it's still in the North Sea, but it's certainly much closer to shore. So we can see that there are potential places to store carbon gases in the rocks, if you like, to return them to a permanent geological storage. The technology exists to do this. However, extracting this carbon dioxide from the atmosphere isn't particularly easy. We then have to transport that carbon gas from where it's produced, in particular like major power sources or major pollutant sources, maybe cement works, power stations, that type of thing, and then transport it to these places where we can inject it into the ground. That's not going to be cheap. The issues with this particular technique are not geological, nor the engineering challenges. The challenges are economic. Are we willing to pay a carbon tax, an amount on every litre of hydrocarbon fuel we use, to be able to safely and securely store the gas that's produced back into the rocks? It's a question that we, as yet, haven't found the answer to.